Hello and welcome to this episode of Physical Attraction, where we'll be dealing with the second part of our question, can a startup build a star? The efforts of startups to develop nuclear fusion technologies. So, Tri-Alpha Energy has received over $500 million and it manages to employ around 150 employees, and it's sustained itself as a company since around 1997. And in their reactor, they can confine plasma for up to milliseconds. So, in the world of nuclear fusion startups, which are obviously a long way behind the mainstream tokamak efforts, this is all pretty good statistics to point to. And what they aim to do is to deploy a form of magnetised target fusion that resembles particle accelerators in many ways. So they're confining spinning plasma in magnetic fields and then accelerating it in their plasma collider, hoping to reliably produce energy when those collisions happen. This is far from the magnetohydrodynamic limit where the plasma behaves something like a fluid. Instead, it operates in this strange transitional regime of plasma behaviour, where tracking the individual motions of at least some of the trillions of particles is important. There are dozens of different parameters that can be adjusted on the machine. Once the spinning blob of plasma is formed from the collisions, it's then bombarded by neutral hydrogen atoms to heat it to fusion conditions, while simultaneously being controlled by the magnetic fields. Given that Tri-Alpha can run a plasma shot every 8 minutes during operation, and given that they're probing this huge parameter space full of strange, difficult, non-linear interactions and complex behaviours, it's perhaps no surprise that they're very into analysing the data that comes out from these experiments. In a high-profile collaboration with Google, they explored the vast numbers of settings for the new machine, looking for interesting behaviour, and they found a more stable regime where, for a few milliseconds, the radiative losses were cancelled out by the energy delivered from the neutral beam injection. So it's clear that Tri-Alpha Energy can produce some fascinating new plasma physics in this extremely complex regime, but it's still impossible to know if some magical combination of magnetic fields, plasma acceleration, and ion bombardment will allow them to exploit these non-linearities to create some sort of holy grail of plasma states that will generate more energy through fusion than it requires to set up. Ball and Parisi, who wrote the book The Future of Fusion Energy, they note that there's another concern with Tri-Alpha Energy, which is in its use of plasma fuel. Most reactors use deuterium-tritium fuel, but Tri-Alpha Energy at present claims that it's going to use proton-boron fuel. So in this reaction, a single proton fuses with a nucleus of boron, which then splits into 3 alpha particles and releases a great deal of kinetic energy, hence the name Tri-Alpha Energy. So there are some advantages to this reaction to be sure. For a start, you'll notice that there are none of those pesky neutrons involved. Alpha particles, which are the products of the reaction, are charged, and therefore they're much easier to stop. They'll stop in most materials. In fact, a few sheets of paper is probably sufficient to stop alpha particles from escaping the device, although you wouldn't want to be the paper in that situation. So you avoid all of these issues of pesky neutron damage to components, and there's plenty of engineering challenges that you no longer need to worry about. You can shield from radiation with a simple thin layer of foil or something like that. And this means that your reactor can be much simpler in its design. What's more, since you're producing these fast-moving charged particles as your products, you might be able to harness energy directly from the motion of those charged particles, rather than using the whole inefficient thermodynamic process, using the heat to create steam that spins turbines, etc, etc, etc. And finally, another advantage of the proton-boron fusion is that the fuels are really easy to come by, abundant, and naturally occurring. A proton is just ionised hydrogen, and you can get hydrogen wherever you want from water. Boron costs about $5 per gram, and there are billions of tons in it in the Earth's crust, in ores like borax. So you don't need to worry about getting a hold of or handling tritium, which is rare or radioactive, and you don't need to worry about using your device to breed more fuel to make the whole process self-sustaining, as they do in the case of ITER and other tokamaks of that kind. So you're obviously thinking, why isn't everyone pursuing proton-boron fusion? It obviously has a whole bunch of advantages compared to the deuterium-tritium reaction. Well, there are reasons, unfortunately, and they are pretty damning reasons. First off, deuterium-tritium fusion has a much lower energy barrier. It's more than 10 times more likely to happen, and can occur at 10 times lower temperatures than proton-boron fusion. When everything is taken into account, you need a fusion triple product that's at least 1,000 times larger with proton-boron fusion, and you'll need to heat the plasma to even higher temperatures than the super-duper hot sun-like temperatures that have been attained in jet and other devices. But the real killer for using other types of fuels comes in the form of radiation from these charged particles. As we've said on the show plenty of times, charged particles radiate when they accelerate, decelerate, change direction, etc. In the case of a deuterium-tritium plasma, most of the energy losses come through turbulence or particles escaping confinement. But for proton-boron fusion, The high charge of the boron nucleus, which has 5 protons and 5 electrons when it's an atom, makes things extremely difficult. For proton-boron fusion, each boron nucleus you have adds 5 electrons to the mix that do nothing but radiate away energy in the plasma. If you do the calculations, you can show that, under fusion conditions, a deuterium-tritium plasma will radiate away just under 1% of the energy it produces as charged particles move around in the device. However, a proton-boron plasma will, under fusion conditions, radiate away perhaps 200% of the energy that it produces. Since it radiates away more energy than it produces, you're never going to get ignition in a proton-boron plasma. In other words, it's never going to be able to operate without an external heating source, because the more energy that's produced by fusion, the more that the particles will radiate away. So this is essentially precisely the same issue that Todd Ryder's paper deals with that we discussed at the end of last week's episode. It may still be possible to harness some energy from proton-boron fusion, but to do this you need to constantly supply some external heating at least. You would then need to be sure that you can capture and harness usefully a huge fraction of the power produced by fusion reactions. Parisi and Ball estimate that, even if your only losses are from this radiation and there's no turbulence, which seems unlikely, then you would need to have heating multiplied by power collecting efficiency of greater than 47% just to produce net electricity. The heating efficiency of neutral beam injections is already down at 30%, so that would need to get substantially more efficient. And converting the energy released from fusion would need to be extremely efficient as well, far more efficient than fossil fuel power plants, for a much more complicated device. And all of that is just to get Q greater than 1. To get the thing to be economically viable is going to be much harder. So proton-boron fusion might be a unique selling point for tri-alpha energy. On paper it has a huge number of advantages as a fuel, being cleaner and requiring less radiation shielding, having more available fuel stuffs and so on, but actually harnessing net energy from these reactions will prove awfully difficult. As it's a fuel you can't really burn, it will always radiate away more energy than it produces to heat itself, and so it can't be ignited in any real sense of the word. Of course, there is a chance that they will in fact just use their same device but for deuterium-tritium runs, and it will be interesting to see where that goes. Lawrenceville Plasma Physics is another startup that hopes to pursue proton-boron fusion, but it will try to do so with big pinch-like devices, arcs of electricity that briefly produce very hot and dense conditions in the plasma. Such devices have been used as neutron sources, as you can get thermonuclear reactions out of them, but they're generally not considered viable for fusion. It acts a lot like a particle accelerator, but these particle accelerators' design mean that currently only around 1 in 25 ions actually undergoes a collision, and so the rate of fusion reactions is very low. Since a lot of energy is put into accelerating particles that then don't end up fusing and releasing energy, you can't afford too many losses. But accelerating the particles itself is, of course, leading to the same radiation issue with proton-boron fusion from before. Lawrenceville Plasma Physics do claim that they'll be able to get around this. They have a particularly ingenious idea. If you can produce high enough magnetic fields with the device, then quantum mechanics kicks in and modifies how electrons gyrate and travel, which may, in theory, reduce the amount of energy that the electrons have. This could then produce that strange plasma that we were talking about, the non-equilibrium state from before, where you'd have hot nuclei that are hot enough to collide and fuse, but cold electrons that won't radiate energy away so effectively. While this idea, using the quantum mechanical magnetic field effect, is really neat, it would require magnetic fields that are unbelievably high to sustain it this way. They would have to be around 1,000,000 Tesla, close to the magnetic fields found at the surface of a neutron star, and more than 1,000 times stronger than anything we've ever created on Earth, at least without utterly destroying the device that created it. Needless to say, this has never been demonstrated as an experiment, and would appear to be an awfully long way off, if it's even at all possible. Without this trick, then, LPP's device will also be doomed to radiate away far more energy than it can produce. Proton-boron fusion is not the only alternative fuel fusion reaction that's been proposed. Helion energy, as its name hints, would use deuterium that fuses with helium-3 rather than deuterium and tritium. So, worth remembering here, tritium is hydrogen with 2 neutrons, so helium-3 is similar, but with 1 neutron replaced by a proton. This produces fewer neutrons, so it simplifies power plant design, and its triple product is not that high. Conditions needn't be too much hotter or denser than you need to produce DT fusion to get this to work. The only problem is that helium-3 is extremely rare. In fact, most of the stock of helium-3 that we actually use comes from tritium that's decaying. It's expensive to get hold of helium-3, and it doesn't exist on Earth in the required quantity. Helion Energy proposed creating their own helium-3 from deuterium-deuterium fusion reactions, but these then produce those neutrons again. And so you can see we're right back where we started again. We need to find some way to produce our fuel with neutrons in a self-sustaining way, and we need to deal with reactions that have some pesky neutron production involved. FirstLike Fusion is another startup based in Oxfordshire, close to perhaps the world's most famous working fusion reactor, JET. They're aiming to succeed in inertial confinement fusion, but they argue that their scientific strategy is based on working with plasma instabilities rather than trying to suppress them with ever more complicated devices. Instead of trying to achieve a perfectly symmetrical implosion of the target, they use computer modelling to design strange, asymmetrical targets, which are then compressed rapidly by shock waves. This approach grew out of the founder's PhD research at the University of Oxford into how these cavities can collapse. The plasma in the target won't be heated uniformly, but FirstLike Fusion hope that an asymmetrical collapse can still produce regions of fusion in the target, where temperatures and densities are high enough, that are large enough to provide net energy. The company aims to be able to rapidly prototype and test new targets, training gradually and iterating towards a perfect target geometry, perhaps aided by machine learning or improved modelling of plasma physics from earlier experiments. So far, they've received £135,000 in funding from sources, including the UK government, and have demonstrated some implosions on asymmetrical targets. One thing that's worth pointing out when we consider FirstLike Fusion is, quite simply, that plasma instabilities are very hard to suppress. This should be clear to any of the dedicated listeners who followed us from early on. The story of inertial confinement fusion and magnetic confinement fusion both essentially involve making bigger and bigger machines that use more and more compression, either via lasers or magnetic fields, to eliminate some of these instabilities. In fact, roughly speaking, the amount of compression needed always seems to be 10 times more than was estimated in the previous generations of device. So while it's possible that some particularly magical configuration of target design or laser firing might overcome these instabilities, or somehow get around their energetic importance, it's this kind of claim that you need to see really firm evidence of before you get your wallet out, and we haven't seen this yet. Lockheed Martin caused a considerable stir when they announced in 2014 that they were working on a compact fusion reactor, with the ultimate aim of using it to power aeroplanes. At the time, the claims were really striking from a very reputable and very engineering and tech-focused company. They said that they would have 5 years for a working prototype and 10 years for a design that was ready for mass production. That was in 2014, so those of you with calendars will be thinking, well, we should have seen that working prototype by now, and no, we haven't. A more recent update in 2017 suggested that this aim had run into problems. Their estimate for the required weight had ballooned from a 20-ton conceptual design to a 2,000-ton prototype. That's difficult to fit on an aeroplane, but if it worked, it would still be less than a tenth of the size of ITER. The secretive Skunk Works department at Lockheed Martin is not short of the technical expertise or funding to become major players, but they are reluctant to publish too many major details. A major issue with tokamaks that Lockheed's compact fusion reactor aims to solve is the issue of the beta limit. So there's only so much plasma that a tokamak's magnetic fields can hold in place, as we talked about last week, and the beta limit essentially tells you how much plasma density you can achieve, which is important for that triple product of density, temperature, and confinement time for a given magnetic field. The beta factor is essentially set by the geometry of the reactor design, alongside the plasma current. For tokamaks, the beta limit is around 0.05 or 5%. This means that to get to a high triple product, you need longer confinement times, higher temperatures, and strong magnetic fields, which usually translates into bigger machines like ITER. Spherical tokamaks can improve the situation. A record beta was achieved by the Korean tokamak START at 0.4 or 40%. So you can see, as we discussed last week, why some companies like Tokamak Energy, spinning out from the MAST device at JET, are trying to investigate whether spherical tokamaks with their higher inherent beta from the geometry will actually be better than the alternatives to tokamaks. Lockheed hopes that their design will have a beta limit approaching 1, meaning that you can have plasma densities 20 times higher with the same magnetic field strength, and this would then allow you for a substantially smaller reactor. So how might this high beta be obtained? Again, it's a matter of geometry. The aim is to find geometries that exploit the plasma's own internal magnetic field, and the currents that flow along its surface as the plasma is confined. This magnetic field would push against the external field that confines the plasma, creating, hopefully, a self-tuning feedback. The further out the plasma goes, so they think, the stronger the B field is that pushes back to contain it. Concepts similar to this were developed in the 1950s under the name of the magnetic mirror, but the magnetic bottles were leaky and containing the plasma particles was difficult. With new geometries, some of which look like many pointed stars or spinning tops laid end to end, it may be possible to limit this leakiness to small regions or cusps, where the magnetic field changes sharply. If these losses can be kept sufficiently low, then, researchers hope, This combination of cusp confinement and magnetic mirrors might allow plasma to be contained for long enough to produce net energy through fusion. So you have to imagine these strange magnetic field lines that look like spinning tops, and then at these edges where the magnetic field changes sharply, you do have some particles escaping, but you try and limit them through clever other arrangements of magnetic fields so that you don't lose too much energy. Yet of course Lockheed are reluctant to publish much experimental data, so beyond some of the computational plasma modelling that initially led them to decide that this was worth pursuing and building a fusion device, it's difficult to know then what precisely techniques they're using and if they've achieved a breakthrough in cusp confinement compared to the original researchers in the 1950s, or even rival companies like EMC², which uses cusp confinement in its polyweld devices. According to Justin Parisi and Jason Ball in The Future of Fusion Energy, Lockheed are pursuing a device that's similar to the magnetic mirror, but with extra coils of magnets placed inside the device, which hope to additionally shape the field and prevent the plasma particles from escaping, except through these cusps. This is theoretically quite promising, but issues arise from the practical implementation of the magnetic fields and the coils inside the device itself. In these thin cusp regions close to the coils, there are likely to be large amounts of turbulence. A cusp, after all, is a sudden change in conditions, big pressure, temperature, and magnetic field gradients, and these big gradients drive turbulent conditions. Having a whole bunch of turbulent plasma right next to your superconducting magnetic coil is an extremely difficult problem. How can you remove what might be megawatts of heat being generated from these coils to keep them superconducting? How can you hold the coils in place when they're being potentially bombarded by plasma? You will evidently need large mechanical supports to keep them there, and you'll also need to run coolant through these supports to keep the internal coils cold and keep them superconducting. But these supports will be extremely close to the hot, turbulent plasma. If plasma touches that solid material, it will probably melt the supports, and impurities will be introduced into the plasma itself. Lockheed has apparently proposed shielding these supports with yet more magnetic fields, but this in turn will be really difficult. The plasma is moving incredibly quickly, at incredibly high temperatures, crossing the device many millions of times every few minutes. So if the shielding only fails to block the few particles a few times, you can expect these supports to disintegrate. But if you don't have the internal magnets, then you'll struggle to prevent particles from escaping through cusp confinement. And of course, even if you do get fusion working, then you have the classic problem of neutrons, which will also serve to irradiate your supports and your coils and your magnets, and if they're this close to the business end of the plasma, then you start to worry about whether even running this thing to produce enough energy and produce therefore enough neutrons is going to destroy it. In other words, while the design may work wonderfully in simulations or on paper and provide good confinement for the plasma, practically building something with these coils actually inside the device may be an impossible engineering challenge. It's certainly going to be a huge one. So, I don't want to go in and say that Lockheed Martin don't know that the plasma physics works. I think, in many ways, a lot of these startups are in a similar position, where they actually have a fairly good expectation that the plasma physics will work and that fusion is possible using their technique. But the issues arise from the ability to build a reactor. I mean, this is true of Commonwealth fusion systems, and maybe Tokamak Energy as well, where they're working on established concepts that have been proved to work, but the engineering challenges are very difficult to overcome because you need to do things that no one has done before. And the fact that in Lockheed Martin's case, both their projections, both for the size of the device and the timeline for its construction, they're continuing to get more pessimistic. Most recently, they're talking about the early 2020s. And this is a familiar story in the history of fusion now, where you start with an optimistic projection for 5 years, and then it becomes 10 years and 20 years and so on. An unclassified briefing in 2017 suggested that a few of the early designs in the cycle had already failed to work as intended. So, success in fusion doesn't happen overnight. It's still an open question as to whether our heightened understanding of plasma physics, our supercomputers, our superconductors, will enable tweaked versions of this magnetic mirror design to overcome the problems that were encountered decades ago. So it's exciting to see a company like Lockheed with a good reputation, a great deal of extremely talented scientists and engineers, taking alternative approaches to fusion seriously. But we should not be convinced that they've cracked it just because it's a private company. And a major part of the reason that people in the mainstream fusion community are sceptical was because of the nature of their initial announcements, where they were talking about having fusion reactors that could fit on the back of trucks within a decade or so. Even the auxiliary equipment to heat the plasma, inject the ions, establish and cool the superconducting magnetic field, etc., would fill a building with today's technology. People will say, well, of course, if Lockheed are investing in it, then it must be some route to profit for them. But you have to remember that there's many routes to profit. For a company as huge as Lockheed, it's perfectly possible for them to invest in plenty of different R&D efforts, knowing that only some of them will succeed, much like the venture capitalists who invest in all of these startups. And in this case, it's not clear that they are expecting this to be their number one belt and braces profit coming from these nuclear fusion reactors. Not at all clear that that is the case. And, of course, if enough people believe that Lockheed Martin are likely to develop nuclear fusion technology, then it probably does good things for Lockheed Martin stock, which is always another thing to think about. So, making bold claims without setting roadmaps that show how it's possible is common in these startups and doesn't win you any friends. The secrecy is, of course, understandable. If you do have a genuine breakthrough that you don't want to share with anyone else, that could be a good sign. But of course, there would be the secrecy there regardless of whether what they're working on is genuinely going to produce nuclear fusion within 5 years, or whether it's just a sort of side project that a lot of the engineers and scientists are passionate about, but that they secretly think probably won't work. We discussed some of the alternative means of pursuing inertial confinement fusion in our episode on NIF, such as the fast drive method or using NIF's large laser in direct drive to illuminate the capsule directly. But there are also major alternative routes towards magnetic confinement fusion. One of them that's particularly worth discussing is the fact that the Stellarator is making a comeback. Remember now the difference between a Stellarator and a tokamak. In a tokamak, the magnetic field that helps to avoid particle drifts is given by running a current through the tokamak's plasma. In the Stellarator, you avoid running any current through the plasma, and you instead try to cancel out these drifts using an extremely complicated, externally imposed magnetic field. So this means that you can't have a simple donut shape for your system anymore, you have to sacrifice that. Instead, you need something that whirls and writhes around, resembling one of those really fast roller coasters, or a complicated, twisting racetrack with lots of ups and downs. It's a Stellarators reactor, for those of you who get that reference. Similarly, the coils and the magnetic fields they produce don't have simple shapes either. Instead, they must also twist and writhe, taking on complex shapes. Physicists generally love symmetry, and it's not because we're obsessively lining everything up to look good like Wes Anderson does when he directs his films. We love symmetry because it simplifies our equations, and because it's easier to predict. If you have a situation that you know is symmetrical, you need to keep track of less information. Imagine something that's symmetric in one direction, so it doesn't matter where you are in that direction. Then your problem becomes two-dimensional, rather than a three-dimensional problem. The equations are simpler to solve, they have fewer variables. Behaviour is simpler to predict, and may be more useful. A torus, a donut for a tokamak, is wonderfully nice and symmetric. The orbits that particles will follow in a tokamak are fairly easy to predict and calculate. But the complex, asymmetric shapes produced by a Stellarator are way more difficult and mind-bending to work with. If you design your Stellarator incorrectly, then the standard orbit of the particles might inevitably cause them to gradually drift out of the device altogether. That's not really a problem, individual particles drifting outside from the tokamak. You're more concerned about disruption. The more complicated the design, the more expensive it will be to build, and the more precisely you need every part of the curvature of your Stellarator to be correct. And of course, the more you have all of these complications, the more things can potentially go wrong. There's a reason that you don't tend to see, in any sort of field, machines with bizarre, artistic curvature in all sorts of strange directions. It's just more difficult to build. If it looks more like a sculpture, then it might not be a piece of scientific equipment. And if every Stellarator takes 20 years to build and is costly, like the main one out there at the moment, the Wendell Steen 7X, then Stellarators are likely to suffer from many of the same problems becoming economical sources of power that currently plague the tokamaks. Designing and building a tokamak and predicting how its plasma might behave, these are already fiendishly difficult tasks. The Stellarator makes these tasks even more complicated. But it's not just about simplifying the design or the calculations. Because tokamaks are relatively simpler, you can usually predict the temperature or density of the plasma in real time when it's running. This allows for some degree of real-time control and feedback over the system. You can respond to changing conditions that you're measuring in the plasma. You can tweak the field, you can tweak the current, you can tweak the heating, in an attempt to get better performance and behaviour from the plasma in a tokamak. But this can only be done because the equations can be solved faster than the plasma is moving and changing around. This kind of feedback and control mechanism, which is part of ITER, will be much more difficult to implement in Stellarators. For a start, you have fewer degrees of freedom in terms of how you're driving the current in the plasma, because there isn't one, and for a second thing, the equations just are much harder to solve. The funky shapes required by Stellarators pose their own engineering headaches, as well as computational and theoretical ones in determining how the plasma will behave. Manufacturing a nice symmetrical coil for a tokamak is relatively simple, although we've already talked about how difficult they actually found it to do this. But manufacturing a complicated, twisty set of magnetic coils for a Stellarator is going to be more difficult and more specialised. Because the shapes and sharp bends in the coils might be required by these 3D coils are complicated, they're also inherently weaker and more prone to mechanical strain. Because the typical forces that act on a Stellarator's coils usually depend on the magnitude of the magnetic field that you try to pass through it, this engineering challenge sets a limit on the maximum magnetic field that you can feasibly use in a Stellarator that's going to depend on the strength of the coils and the Stellarator geometry that you're using. So if your Stellarator needs loads and loads of really sharp kinks, and your coils are particularly weak, then you'll have to compensate with a smaller consequential magnetic field. So given all of these caveats, why are people still enthusiastic about Stellarators? There are several reasons. There's no plasma current to be disrupted, so disruptions simply aren't a problem. And with no plasma current limits that are set in place, you won't get large kink instabilities either. In fact, in general, the failure mode for Stellarators is less damaging than that for tokamaks. What happens in Stellarators is that plasma particles tend to drift out towards the walls, gradually cooling the plasma and leading to a loss of confinement. So they can be leaky bottles. But you don't get quite violent disruptions as you do with tokamaks, which could potentially damage the equipment. If, for example, ITER is ruined by disruptions, they prove hard to predict or mitigate, or every few months, every few days you get a disruption and only 5 or 6 of them is enough to destroy the vacuum vessel of the machine, etc., then looking for a reactor with a less damaging failure mode could be an advantage. And it also circumvents some of the material science challenges that we need to talk about earlier. I mean, suddenly the first wall and the diverter don't need to be quite so strong to stand up to some of the punishment from disruption. It may be easier to get net energy out of a Stellarator once you get it working, and if confinement times are long enough. Once you've heated the plasma to the ignition stage, such that the energy to drive more fusion reactions is provided by fusion reactions alone, then you don't need to provide the plasma with any more energy. You don't need to drive the plasma current, as you do in a tokamak. In fact, the main source of energy consumption would probably be in keeping the superconducting magnets cool, as, once the current is flowing through them and their magnetic field to confine the plasma has been established, they won't require any more energy either. The fact that Stellarators are like this, that they essentially intrinsically operate in a steady state, means that it's easier for them to withstand longer pulse durations than other devices. Stellarators have been run that have been able to confine plasmas for almost an hour, which is substantially longer than the few minutes that's set at the record for tokamaks, although the triple product, and hence the fusion energy that you might produce, is much lower for Stellarators than the tokamak record. The final reason that people are quite excited about Stellarators is the idea that perhaps the complexity of the Stellarators' design could be an advantage in itself. Yes, it means that the behaviour of the plasma is more difficult to model and understand, but it also gives you more degrees of freedom, more knobs that you can twiddle with, in the hope of finding a perfect combination of parameters. As our ability to computationally model how plasmas will behave gets better, it may be possible to work out how they will behave in extremely complex magnetic field geometries. Machine learning algorithms and optimization algorithms could even try to explore this huge space of different Stellarator designs in an attempt to determine which design will produce the best performance, before the Stellarator is actually built at all. It may seem a little unlikely that there will exist some magical, fiendishly complex arrangement of magnetic field lines that proves to be just perfect at confining hot, dense plasma for months on end for fusion to work. You're effectively hoping to find that perfect design for a magnetic field that will cause all of the little drifts to perfectly cancel themselves out. But the huge array of different designs one can imagine for a Stellarator means that it's very difficult to rule out this idea entirely. The largest ongoing Stellarator project at the moment is probably the Wendell Steen 7X, which was planned from 1997 and opened in Germany in 2015. Like many other fusion projects, it probably won't surprise you to hear that it ran over schedule and over budget, eventually coming in with a price tag of €1 billion. Determining the complex, twisty design of the Wendell Steen required supercomputer time and the latest magnetohydrodynamic simulations. It's in the early phases of its operation at present, but it's already reaching triple products that are close to what JET has achieved, and confinement times longer than JET has managed. By 2021, they are hoping that the device will be continually operated for 30 minutes. And remember, this continuous operation is going to be key for any fusion plant to be economically competitive, whether it's a tokamak or a Stellarator. As the big Stellarator project, There's of course a lot riding on this for this kind of fusion reactor and its advocates. If ITER fails or stalls while Wendell Steen performs better than expected, funding might end up getting diverted into Stellarator research projects. On the other hand, if the Wendell Steen performs less well than expected or encounters some new problem, you can expect the Stellarator revival to fall out of favour once again. So how is the Wendell Steen doing since it was switched on? Here's the project's scientific director, Thomas Klinger. He said, quote, "The Wendell Steen Stellarator project is following a stepwise approach for full operation, much like ITER will. We have conducted 2 experimental campaigns, and are now preparing for the 3rd. We started the first experimental campaign in 2015 with somewhat of a naked machine. The machine was constructed, successfully commissioned, and had created first plasma, but at that time it was not yet equipped with the proper plasma-facing wall components, or a diverter. Instead, it just had a limiter and a metal wall. Over the following 14 months, we worked on the diverter, the machine's exhaust system for extracting heat and particles, which enables us to control the density and the purity of the plasma. In addition, we installed graphite tiles in the areas of the vacuum vessel with higher heat loads. The diverter and the in-vessel cladding were the real gate openers. We could increase the heating power and achieve much longer plasma discharges, but we still had a problem with obtaining high plasma densities. We identified the problem. Oxygen impurities emanating from water released by the graphite tiles were strongly emitting light. We solved the problem by conducting wall conditioning by boronization, so oxygen is being pumped out now by boron. All of a sudden we had clean plasmas, the oxygen light emission dropped by a factor of 10, and we were able to ramp up plasma densities to much higher values without loss of confinement. Consequently, in our most recent campaign in 2018, we could extend the pulse duration, achieving higher plasma temperatures and densities. With input heating of 200 megajoules, we achieved a 30-second plasma at 6 megawatts, and at reduced power, we achieved a 100-second plasma at 2 megawatts. These are amongst the best results achieved so far by any Stellarator. More recently, in 2018, the Wendell Steen second phase of experimentation was completed, and it's now being upgraded to reach that peak performance with, hopefully, confinement times up to 30 minutes. Highlights from this first phase included reaching the maximum triple product ever achieved by a Stellarator, and successfully testing the graphite-plated first wall and the diverter for the Stellarator. As I write this in 2019, it's still undergoing the upgrade for the next phase of experimentation, including introducing a water-cooled first wall and diverter system so that it can operate at higher energies and for longer times, without melting down these components. There is clearly no shortage of alternative dark horse projects aiming towards nuclear fusion. Each has its own charms, challenges and quirks. Each can point to its own unique selling points. Many are backed by millions of dollars of venture capital funding, and attract disaffected plasma physicists left out in the cold by the focus on ITER. Some offer tweaks to the mainstream designs, some resurrect ideas that were abandoned decades ago in favour of tokamaks, while others venture into more radical, unproven territory. Many have compelling scientific arguments surrounding why they might succeed, and others have compelling scientific arguments about why they might fail. And they all share the same compelling economic argument that nuclear power, and fusion in general, will require smaller reactors than ITER if it's ever going to be commercially viable. In many ways, away from ITER, NIF and the other big tokamaks, the landscape of fusion today resembles the 1950s more than anything else. Then too there were dozens of different ideas for advancing fusion being enthusiastically pursued by each of their devotees, and it was difficult to say which, if any, had the best chance of ultimately succeeding. The naive optimism of the 1950s, that fusion might be easy to achieve, has been replaced with a tempered techno-optimism. Now we know more, we can understand the challenges, perhaps. Now we have access to high-temperature superconductors and machine learning, as well as decades of plasma physics results and experience, we aren't going into a landscape that's totally unknown. Different devices and different approaches painstakingly have been able to achieve continuous improvements in fusion over the decades, without hitting a wall that no one can find their way around. Fusion then seems to be merely extremely difficult, and not impossible. Yet ultimately we shouldn't kid ourselves that what they're predicting is extremely likely to come to pass. Published science from the startups is not always particularly complete, and often doesn't back up the hype PR claims that they'll have viable fusion reactors in 10 or 20 years. The triple products achieved by these machines are, universally, many thousands of times smaller than those achieved by more established rivals like tokamaks and Stellarators. Many flowers may bloom in the fusion startup world, but they're relying on an astonishing amount of luck, or seeing some design that's millions of times better than what's been pursued for decades, to overtake tokamak. The classic retort from the more mainstream fusion scientists when they see the giddy claims of these startups is, what is your best fusion triple product? And for many of the startups considered so far, if they even have measured it, it will be 10,000 or 100,000 times less than the record performance achieved by JET in 1997. If it took tokamaks decades of research effort on behalf of many people to achieve these increases in performance, argue the mainstream scientists. I mean, why should we believe that this new device will be any different? And we've seen over and over again, through fusion history, tales of scientists who thought their devices were far closer to achieving net power from fusion than they really were, or who simply oversold the potential of the device to get more funding. So perhaps the most promising candidates are those that tweak the tokamak design with new, high-temperature superconducting magnets. They operate with a far greater degree of established science behind them. But even these startups still have a long way to go, and making tokamaks smaller comes with its own material science challenges. Many of the issues with building, e.g. a diverter that can withstand astonishing heat fluxes from the fusing plasma, actually harnessing the energy once you've produced it, managing disruptions, they are likely to remain problematic even for smaller tokamaks. And once again, we need to remember that producing electricity from fusion and producing net electricity from fusion are deeply different. Not to mention, of course, that making it in any way profitable is a long, long way away. It can seem amazing that, nearly 70 years after the first promises were made that fusion would produce our energy within a few decades, and after countless promises of this kind have been broken, there are still optimists out there who can say it with a straight face. But then again, perhaps it's not so surprising. Of course, it will always remain possible in science that there is some shortcut, some brainwave, some magical design, some new, weird and unexpected plasma phenomenon that allows for vastly better performance and shortcuts all of this difficulty. You can't rule out things like this from happening in science. They have before, after all. And this is likely the spirit that a lot of the people in these startups adhere to. Never say never. After all, to believe you can succeed where decades of research, generations of plasma physicists, and billions of dollars have yet to succeed, you need a sunny disposition. Thank you for listening to this episode of Physical Attraction. Next week we are going to finally conclude the Fusion series with a look back over everything that we've learned and into the future. You can give us comments, feedbacks, anything you like on www.physicspodcast.com, where you'll find the contact form, the link to our Patreon where you can download subscriber-only episodes, the link to our PayPal, and you'll be able to contact us via the contact form. All goes to my email. I read it all and respond to the stuff that makes vague, coherent sense. You can follow us on Twitter at PhysicsPod and Facebook Physical Attraction. Until next time then, take care.